You think you see stars when you look up at the night sky. Thousands of bright points scattered across the darkness, some steady, some twinkling, some bright, some dim. You think you're seeing distant suns just as they are, shining across the void. That's what everyone thinks. That's what it looks like. But here's what you need to understand. You're not seeing stars. Not really. What you're seeing is an optical illusion created by your eye and the atmosphere. The bright points you perceive have almost nothing to do with what the stars actually look like. This is not poetry. This is not metaphor. This is optics and physiology and atmospheric physics. And when you understand what's actually happening, when you look at the night sky, when you trace the path of light from a distant star to your retina, you discover that almost everything you think you're seeing is false. The twinkling is false. The size is false. The sharpness is false. Even the number of stars you see is wrong. What reaches your eye is real light from real stars. But what your brain constructs from that light is a heavily processed, distorted representation that bears little resemblance to reality. Let me show you exactly what's happening. Start with a basic fact. Stars are far away, not far in the sense that you need a telescope to see detail, far in the sense that they're physically impossible to resolve with the naked eye. The nearest star to Earth after the Sun is Proxima Centauri, 424 light-years away. That's 40 trillion kilometers. And Proxima Centauri is a red dwarf, much smaller than the Sun. Even if it were right next to Earth, it would still be tiny. But it's not next to Earth. It's 270,000 times farther away than the Sun. Now think about angular size. How large does an object appear in your field of view? That depends on its actual size and its distance. The farther away something is, the smaller it appears. Stars are so far away that even the largest ones appear vanishingly small. Betelgeuse, one of the largest stars we know, has a diameter about 900 times that of the Sun, but it's 550 light-years away. Its angular size, as seen from Earth, is about 0.05 arcseconds. That's 0.00 or more futur degrees. Your eye cannot resolve anything smaller than about 60 arcseconds under ideal conditions. Betelgeuse appears 1,200 times smaller than your eye's resolution limit. What does this mean? It means that no star, not even the largest, closest ones, should appear as anything other than a mathematical point to the naked eye. You shouldn't see a disk. You shouldn't see size. You should see nothing, or at most, an infinitely small point of light. But that's not what you see. When you look at a bright star, you see a definite shape, a fuzzy circle, a point with extent. Why? Because your eye is not a perfect optical instrument. It's a biological system with limitations and quirks. And one of those quirks is diffraction. When light passes through a small opening, it spreads out. It bends around the edges. This is a fundamental property of waves. And light is a wave. When light from a star enters your pupil, which is a circular aperture a few millimeters wide, it diffracts. The light spreads out into a pattern, a central bright spot surrounded by fainter rings. This is called an airy disk. The size of the airy disk depends on the wavelength of light and the diameter of your pupil. For visible light and a typical pupil size, the airy disk spans several arcseconds. That's larger than your eye's resolution limit. So even though the star itself is a point source, the diffraction pattern created by your pupil makes it appear to have size. What you're seeing is not the star. What you're seeing is the diffraction pattern of starlight passing through your eye's aperture. But it gets worse. Your eye is not a perfect lens. The cornea and lens inside your eye have imperfections. Slight irregularities in shape, variations in refractive index. These imperfections scatter light. They create additional blur. They add to the diffraction pattern, so the point of light from a star gets smeared out even more. The result is that every star, regardless of its actual size, appears as a fuzzy blob of approximately the same angular size, determined not by the star but by the optics of your eye. Now add the atmosphere. Light from a star travels through vacuum for years, arriving at Earth as a nearly perfect plane wave. Then it hits the atmosphere, and the atmosphere is not uniform. It has layers of different temperature, pockets of different density, turbulent mixing, wind. All of these variations cause the refractive index of air to change from place to place and moment to moment. And when light passes through regions of different refractive index, it bends. It changes direction. This is atmospheric refraction, and it doesn't happen once. It happens continuously as the light passes through kilometers of turbulent air. The path of the light wobbles. The direction changes randomly many times per second. The wavefront, which was smooth and flat in space, becomes distorted and chaotic by the time it reaches your eye. And because the distortion changes rapidly, the image of the star appears to jump around, to shimmer, to twinkle. Twinkling is not a property of stars. Twinkling is atmospheric turbulence distorting the light. If you observe from space, above the atmosphere, stars don't twinkle. They shine steadily. The twinkling you see from the ground is entirely an artifact of Earth's atmosphere. It tells you nothing about the star. It tells you about the air between you and the star. But atmospheric effects do more than make stars twinkle. They also blur the image. The rapid changes in refraction cause the light to spread out over a larger area. Instead of all the light hitting a single point on your retina, it gets smeared across multiple points. This is why stars appear larger and fuzzier when viewed near the horizon, where the light passes through more atmosphere. The increased atmospheric path length increases the distortion. And here's something most people don't realize. The atmosphere doesn't just blur starlight, it also changes the color. Different wavelengths of light refract by different amounts. Blue light bends more than red light, so when a star's light passes through the atmosphere at a steep angle, the different colors get separated slightly. The star appears to have colored fringes. Sometimes you can see a star flash red, then blue, then white, as atmospheric turbulence causes different wavelengths to dominate. This is atmospheric dispersion. It's the same effect that creates rainbows, and it's another layer of distortion between you and the actual star. Now let's talk about what you're actually seeing when you look at a specific star. Take Sirius, the brightest star in the night sky. When you look at Sirius, you see a single brilliant point of light. But Sirius is not a single star. It's a binary system. Two stars orbiting each other. Sirius A, a bright white main sequence star, and Sirius B, a faint white dwarf. Sirius B is only about 8.6 arcseconds away from Sirius A. That's well within the resolution limit of a telescope. But to your naked eye, the two stars are completely unresolvable. You see one point of light. The light from both stars hits the same diffraction pattern, the same blur, the same atmospheric distortion. Your eye combines them into a single image. How many other stars you see are actually multiple stars? Many, probably most. Alpha Centauri, the third brightest star, is actually 3 stars. Castor, in Gemini, looks like 1 star, but is actually 6. Mizar, in the Big Dipper, is 4 stars. The number of binary and multiple star systems is enormous. But your eye can't resolve them. You see single points where there are actually 2, 3, 4, 6 separate stars orbiting each other. And then there are planets. When you look at a bright object in the night sky, can you tell if it's a star or a planet? Not easily. Venus, Jupiter, Mars, Saturn, these all appear as bright points, just like stars. The only difference is that planets don't twinkle as much, because planets have angular size. They're close enough that they appear as tiny disks, not points. And because they're disks, atmospheric turbulence averages out across the surface. Different parts of the disk twinkle at different moments, so the overall brightness stays more constant. But this is a subtle effect. Most people can't reliably distinguish planets from stars by eye. So when you look at what you think is a star, it might be a planet, it might be multiple stars, it might be a galaxy. The Andromeda Galaxy, 2.5 million light-years away, appears as a faint fuzzy patch. To the naked eye, it looks like a star that's slightly out of focus. But it's not a star. It's 200 billion stars, so distant that their combined light reaches you as a barely visible glow. You're seeing an entire galaxy, and it looks like one blurry star. Now let's address something even stranger. The light you're seeing from stars is old. Light travels at a finite speed, 299,192 kilometers per second. Fast, but not infinite. The light from the sun takes 8 minutes to reach Earth. So when you look at the sun, you're seeing it as it was 8 minutes ago, not as it is now. The sun could have exploded 7 minutes ago, and you wouldn't know yet. The light from that explosion is still on its way. For stars, the delay is far longer. Proxima Centauri is 4.24 light-years away. The light you see tonight left that star 4.24 years ago. Sirius is 8.6 light-years away. The light you see left in 2016. Betelgeuse is 550 light-years away. The light you see left in the 1470s before Columbus sailed to America. When you look at distant stars, You're looking back in time. You're seeing them not as they are, but as they were when the light began its journey. And here's the disturbing part. Some of the stars you see might not exist anymore. Betelgeuse is a red supergiant nearing the end of its life. It could explode as a supernova at any time. It might have exploded already. The explosion might have happened 200 years ago, but the light from that explosion won't reach us for another 350 years. So when you look at Betelgeuse tonight, you might be seeing a star that has already died. You're seeing a ghost, an image of something that no longer exists, preserved in light that's been traveling for centuries. This applies to every star you see. The farther away they are, the older the light. Stars thousands of light years away show you images from thousands of years in the past. The night sky is not a snapshot of the present. It's a time machine, a collection of images from different moments in history, all arriving at your eye simultaneously because the light took different amounts of time to get here. Now think about what this means for constellations, the Big Dipper, Orion, the Southern Cross. These patterns are accidents of perspective. The stars in a constellation are not actually near each other. They're at vastly different distances. The stars in the Big Dipper range from 58 to 124 light years away. They're not a group. They're not physically related. They just happen to lie in roughly the same direction as seen from Earth. And the light from each star left at a different time in the past. When you look at the Big Dipper, you're seeing some stars as they were 58 years ago and others as they were 124 years ago. The pattern you perceive exists only from Earth's perspective and only at this moment in cosmic time. And the patterns are changing. Stars have their own motion through space. They're not fixed. Over thousands of years, the constellations distort and shift. The Big Dipper 100,000 years ago looked different. The Big Dipper 100,000 years from now will look different. The patterns you see are temporary. They exist for a brief window of time in the life of the galaxy. Humans have only been looking at these patterns for a few thousand years. That's nothing. In cosmic terms, it's an instant. The constellations, you know, are fleeting arrangements that will dissolve and reform into new patterns as stars continue their motion through the galaxy. Let's go deeper. When you see a star, what you're actually detecting is photons, individual particles of light that traveled across space and happen to hit your retina. Each photon carries a tiny amount of energy. For a dim star, only a few photons per second enter your pupil. For a bright star, millions. But either way, the photons are discrete. They arrive one at a time. Your retina detects them one at a time, and your brain integrates these individual detections into a continuous perception of light. But here's the thing. The photons you detect are an infinitesimal fraction of the total light emitted by the star. A star like the Sun emits 10^45 photons per second. Most of those photons fly off into space and never hit anything. A tiny fraction happens to travel in the direction of Earth, and of those, only a minuscule number happen to enter your pupil. You're detecting perhaps one photon out of every 1020 emitted by the star. You're seeing a statistical sample, not the full output. And your brain constructs an image from this sparse, random sampling of photons that happen to reach you. And the energy carried by those photons is absurdly small. A single visible light photon has an energy of about 10 micro 19 joules. That's 0.1 joules. When you look at a dim star, the total energy entering your eye might be 10^15 watts. That's a femtowatt, 1/quadrillionth of a watt. Your eye is detecting light so faint that it's measured in individual photons, and yet your brain interprets this as a bright, steady point of light. The sensitivity of your visual system is extraordinary. But it also means that what you perceive is heavily processed, heavily interpreted, far removed from the raw physical stimulus. Now consider color. Stars have different colors. Betelgeuse is red, Rigel is blue, Sirius is white. These colors are real. They correspond to the temperature of the star's surface. Hot stars are blue, cool stars are red, but the colors you see are not the star's actual colors. They're the colors your eye perceives after the light has been filtered by the atmosphere, diffracted by your pupil, and processed by your retina and brain. Your eye has 3 types of color receptors: cones that respond to short wavelengths, blue, medium wavelengths, green, and long wavelengths, red. When photons hit these cones, they trigger chemical reactions that send signals to your brain. Your brain interprets the relative strength of these signals as color. But this process is not a direct measurement of wavelength. It's an approximation, a reconstruction. 2 different wavelength distributions can produce the same perception of color if they trigger the same pattern of cone responses. This is called metamerism. The color you perceive is not a unique property of the light. It's an interpretation created by your visual system. And for stars, the situation is even more complicated. Most stars emit light across a broad spectrum of wavelengths. A hot blue star emits blue, green, red, infrared, ultraviolet all at once. Your eye integrates all these wavelengths, weights them by the sensitivity of your cones, and produces a single perceived color. But that perceived color is not the star's actual color. It's a summary, a simplification, a best fit interpretation created by your brain. The actual spectrum of the star is far richer and more complex than the single color you see. And then there's magnitude, brightness. When you look at the night sky, some stars appear bright and some appear dim. You assume that bright stars are either larger, closer, or more luminous than dim stars, and generally, that's true. But the brightness you perceive is not a direct measure of the star's luminosity. It's affected by distance, by atmospheric extinction, by interstellar dust, by the sensitivity of your eye. Astronomers measure brightness using a logarithmic scale called magnitude. A difference of 5 magnitudes corresponds to a factor of 100 in brightness. Sirius, the brightest star, has an apparent magnitude of 1.46. The faintest stars visible to the naked eye have a magnitude of about +6. That's a brightness ratio of about 1500 to 1. But this ratio is apparent brightness, not intrinsic luminosity. A dim-looking star might actually be incredibly luminous but very far away. A bright-looking star might be relatively faint but very close. Sirius appears bright not because it's the most luminous star, but because it's close, only 8.6 light-years away. Deneb in the constellation Cygnus appears about as bright as Sirius, but Deneb is 2,600 light-years away. It appears similarly bright despite being 300 times farther away because it's intrinsically much more luminous. Deneb is emitting about 200,000 times more light than the Sun. If you swapped Deneb and Sirius, Deneb at 8.6 light-years would be brighter than Venus. It would cast shadows at night, and Sirius at 2,600 light-years would be invisible to the naked eye. So when you look at the night sky and see bright stars and dim stars, you're not seeing a true representation of stellar luminosity. You're seeing a confused mixture of distance effects, intrinsic brightness, atmospheric conditions, and the logarithmic response of your eye. The brightness you perceive is an unreliable indicator of the star's actual properties. Here's the bottom line. When you look at the night sky, you think you're seeing stars, but what you're actually seeing is diffraction patterns created by your pupil, optical aberrations from your cornea and lens, atmospheric turbulence causing twinkling and blur, atmospheric dispersion separating colors, multiple stars blended into single points, planets masquerading as stars, galaxies appearing as fuzzy stars, light from hundreds or thousands of years in the past, stars that might no longer exist, photons sampled statistically from an enormous emission, colors interpreted and simplified by your visual system, brightness distorted by distance and atmospheric extinction. Not one of these is the actual star. What you see is a heavily processed, heavily distorted, heavily interpreted illusion created by the combination of physics, biology, and perception. The real stars, the actual physical objects, are inaccessible to your naked eye. They're too far, too small, too faint. What reaches you is light, ancient light, bent and scattered and distorted by the time it arrives. And your brain takes that distorted light and constructs an image that feels real, that feels direct, but is in fact a simulation, an approximation, a best guess at what might be out there based on fragmentary, degraded information. This is not to say stars aren't real. They are. They're massive balls of plasma undergoing nuclear fusion, emitting light and heat and particles across the electromagnetic spectrum. They exist. But what you see when you look at the night sky is not them. It's the shadow they cast in photons, filtered through atmosphere and optics and biology, arriving at your consciousness as a simplified, abstracted representation that your brain labels as stars. The night sky you see is an illusion, a beautiful illusion, a useful illusion, but an illusion nonetheless. And once you understand that, once you see through the illusion to the mechanisms creating it, you can never look at the stars the same way again. You'll know that the twinkling is air, that the size is diffraction, that the color is interpretation, that the light is ancient, that the image is a lie, not a malicious lie, not a deceptive lie, but a lie in the sense that it is not the truth. It is a representation, a model, a story your brain tells you about distant points of light that you will never truly see. And here's what makes this profound. Every human who has ever lived has seen the same illusion. Ancient civilizations looked up and saw the same patterns. They saw the same twinkling points. They constructed myths and navigation systems and calendars based on these illusions. The entire history of astronomy, of navigation, of timekeeping is built on observations of images that are not real, on light that has been distorted and delayed and processed beyond recognition. And yet from these distorted images, we learned the truth. We figured out that stars are suns, that they're at different distances, that they move through space, that they're born and die, that they're made of the same elements as Earth. We decoded the illusion. We extracted real information from false images. We measured distances from parallax. We determined compositions from spectra. We calculated masses from orbital mechanics. The images were lies, but the physics was true, and that physics derived from careful analysis of distorted light revealed the universe. This is the power of science, not accepting what you see at face value, not trusting your immediate perception, but analyzing, measuring, questioning until you understand the mechanisms creating the appearance. The stars you see are illusions, but the stars that exist are real, and the path from illusion to reality is through physics, through understanding light and optics and atmosphere and time, through recognizing that your senses are limited, that your perceptions are constructed, that reality is deeper and stranger than appearance suggests. So the next time you look up at the night sky, remember what you're actually seeing, not stars, but echoes, not present reality, but ancient light, not direct observation, but heavily mediated interpretation. The universe is not hiding from you, but it is not showing itself directly either. What you see is filtered, distorted, delayed, processed, and that filtered view is all you get. The real universe, the actual stars as they exist now, is forever beyond your direct perception. You see only shadows, only traces, only the stories your brain constructs from fragmentary evidence. But those stories, imperfect as they are, point to something real, and that is enough.